then we definitely have kinematic equations that we want to have on there. So V final equals V initial plus AT. I'm going to use S as a general position variable. You can put X or Y, but you just have to remind yourself that you can use X or Y in this. So S final equals S initial plus V initial T plus 1/2 AT squared. See, you're okay with S being X or Y?
Okay.
And then same thing goes here, V final squared equals V initial squared plus 2A change in S. So S is just a generic, we don't know if it's X or Y, it's just a position. So this just is telling you that you can use X or Y, but not both in the same equation. You have to pick X or Y, and you use all X values or all Y values. So you can write them just as V final equals V initial plus AT, X final equals X initial plus V initial T, AT squared, and then V final squared equals V initial squared plus 2A change in X. You can write them that way and just remember to remember that you can use Y as well.
Okay.
So those three things I have. What else have you gone over? So this will help you with graphs, position graphs and stuff. This would help you if you want to have like a problem-solving strategy. You could kind of write that down.
Mm-hmm.
These will definitely help. I definitely have those. Vectors. How are you?
Yeah, we'll probably go over those on the test.
So you're pretty good with like vector math, like addition and subtraction?
Pretty good. You alright?
So you have vector A, vector B. How would you add those?
You take the end of B and put it at or the beginning of B and put it at the end of A.
Yeah, so you can maybe, if you want to draw a little diagram of this and say, well, this is A plus B. And then if you want to do A minus B, you could draw something like this. This is negative B. A minus B. Just to remind you that all you do is flip. You could write it as like A minus B equals A plus a negative B.
Okay.
And then maybe one that was a little bit more new is taking this idea where you have, this is our vector C. It has some magnitude and it's at an angle theta. And you want to break it into X and Y components. So we talked about this last time, right?
Mm-hmm.
So Cx would be equal to what?
Let's see. Pythagorean theorem.
Well, that's what you want to do at first, right?
Yeah.
But in this case, you don't start out knowing either Cx or Cy.
Right.
So you can't use them to solve for each other.
Okay, it's let's see, sine of theta.
Okay. Which one does sine go with?
Opposite over hypotenuse.
So it's this one.
Yeah.
So we can say, well, the sine of theta equals cy over c, magnitude of c, so that's the length.
Okay. So we want the cosine,
Okay?
so,
Cosine of theta equals cx over the magnitude of c. So what does cx equal to?
see, cosine times the minus the magnitude of c.
Yep. So if c was a direction of, or was a length of 11 with the direction angle of 28 degrees, what's cx? Here, I'll draw that. 11, direction angle 28 degrees.
So it'd be 11 times cosine of, oh, wait. 11 times the cosine of 28?
Yeah, exactly.
Okay.
And then cy,
C, B, sine times C. So sine of 28 times 11.
yep. Okay, so you can, if you wanted to draw a picture like that or something, it's a good, another little concept to review. One thing to keep an eye out is when a vector is drawn like this. So this is 50, it says this angle is 32. What changes here if you try to find the x and y components? So this is x, this is y.
I forgot.
So you just have to watch which side your angle's on.
Mm-hmm.
So this time your x is opposite your angle, right?
Uh-huh.
So this would actually be sine of 32 degrees would equal to the x over the hypotenuse.
Okay.
So this time x equals 50 sine 32.
Okay.
Even though we think of sine, we usually think of the y-axis. Y would be equal to 50 cosine of 32. So just make sure that when you draw your angle, or like when they give you an angle, that you make sure which side is opposite, which side is the adjacent,
Alrighty.
before you solve them. So that's decomposing vectors into x and y. You remember seeing vectors in like, C theta cx equals c cosine theta, cy equals c. Just kind of a review on that. I'll draw them in here, cx, cy. Now, one other thing, what's the benefit of doing this when you're trying to add or subtract vectors?
I don't know.
So when you have it this way, say you're trying to add, you're given an angle like this, and maybe it's 15, angle of 45 degrees. And then you're like, well, I want to add another vector that's like this, and I know this one is 20 at an angle of, let's call this 52 degrees or something like that. Well, you know what your resultant vector looks like. So this will be your result. But how long is it? You have no idea, right?
Mm-hmm.
And it's almost impossible. I mean, it's not almost impossible, but it's a lot more difficult because you end up having to use the law of cosines to find out its length. And then the same thing goes for its angle, right? it has some angle in there, but you don't know what it is because you end up having to use law of cosines and law of sines to solve for it. So instead, when you have that kind of a situation, if you just break it down, this has an x component and a y component that are pretty easily found, right? Oops. This is x, y. This one also has an x component and a y component, which are pretty easy to find. And if you add your x plus y plus x, you get the same resultant vector, right?
Yeah.
Now, if you take it one step further, turns out if you say, well, let's take this x component, let's just add this x component to it right away. So we add those two together.
Okay.
And then let's add this y component. Well, that goes up. And then the other y component goes down. So we added x plus x, y plus y. It gives us this vector, which is the exact same as if you add either the vectors by themselves or their x component in x, y, x, y.
Uh-huh.
It'll give you the exact same vector. So you just add your x components and your y components, and you get your resultant vector. So, and it doesn't matter how many vectors you're adding or subtracting that way. So it could say, well, give me a plus b plus c plus d. You say that's going to be a real pain if I've got vectors looking like this, you know, to try to use the law of cosines on it and figure out what that resultant vector is.
Yeah.
But you can say our E is equal to that. Or you can just break it up and you say, well, EX is going to be equal to AX plus BX plus CX plus DX. So that gives you some value. And then EY is going to be equal to AY plus BY plus CY plus DY. Since all of these values are just scalar quantities like this, you can add them up real quick, and then you end up with an EX and an EY. And the way that, so now you've got an EX and EY, so you can draw those. You say, well, EX looks like this, and EY looks like this. So what's the resultant vector going to look like?
Just between them.
Yeah, so it'd be, you can draw your little parallelogram here, draw it out here. So this is going to be E. Now, what if you want to find the angle here?
When you do, let's see, the tangent?
Yeah. So you know that you've got the tangent of theta equals what over what? So which side is the opposite?
It's the EY side.
Yeah. Over adjacent.
Yeah.
So if you want to solve for theta, theta equals inverse tangent of EY over EX.
Okay.
Then what if you want to find the length of E, so the magnitude E?
Then we take the EX squared plus EY squared.
That'll actually give you this squared,
Yeah.
so then you can just do this.
Square root, yeah.
So that's a much quicker process than using the law of cosines and the law of sines to try to figure out what E would eventually be. It'll give you the exact same answer.